Hello. So I think it's time to start, and yeah, some more might be joining, but I will start now. So welcome and to this talk. This talk is about perhaps one of the most common security challenges we face as members of DevOps teams or some kind of architect or security advisor, and at its core, it looks like this. And it's simple. We have a server, and we have some server resources that we want the client to access in a secure way. And a typical example of this is an API, and we will start focusing on that. So let's say you have a business partner that want to integrate with you, and they suggest to use HTTPS and an API key. And you get the question, is this secure enough? Then what would your answer be? And if that is not secure enough, what should you use instead? So, and before we dive into that, my name is Tobias, and if you search for me online, you might find this. That's my LinkedIn profile, and I've been at Omega Point for some years now doing penetration testing and security reviews, and have had the benefit of seeing system integrations at different environments or different kinds from both the offensive and defensive side. But as we all know, LinkedIn, that's just marketing, so you might use some AI to dig out the truth about me, and then you might get this. And yeah, well, it looks valid to me, so enough about that, and we go back to API security. And the basic defenses that we have can be grouped into two: infrastructure layer security and application layer security. And we will go through those defenses here, and we will start with the basics and add more defenses as we go along, and see what motivates more complex things like OAuth and sender-constrained access tokens. So we start with the basics, the infrastructure protections, and I know classic IP-based security might be boring for us as a modern cloud-native DevOps organization, but before you sort of zone out for this slide, remember this. Attackers will find you on the internet, so only expose APIs publicly if you need to do that, and use private networking to avoid a lot of those sort of garbage requests that will hit public endpoints. But if you do apply that, remember that network defenses is just the first layer of defense, and you should never assume that all clients on the network are trusted. So we need to add more security and more defenses. So we add transport and application layer defenses. And next we will look at transport layer security, and that it's vital to have strong transport layer security for the applications layer defenses that we add later on. And so it's important to use end-to-end strong transport layer security for all requests, and to that will provide us with confidentiality and integrity for the request we send. And for system integrations, today it's quite possible that you can require TLS 1.3 only. And if you do need to support 1.2 for legacy reasons, I mean, it's quite common, then it needs to be hardened. And there are good guides for that. And for system integrations, where no humans are involved, just machine to machine, it can be restricted to just 4 ciphers. And there's more to say about hardening transport layer security, and we won't go into details. And there are good tools you can use for scanning and evaluating your transport layer security. And one such tool that we use during penetration testing is from SSL Labs that you can use for public endpoints. So that seems pretty easy to just doing strong transport layer security. And so one issue here that we have is the end-to-end aspect. And if we have like this, we have the client and the API here, the server, and we have good HTTPS end-to-end. But then also remember the infrastructure protections and using firewalls and stuff is also important. So we of course apply that. We should always have something in front of our service that we build. So we add that, and to use good security features with those kind of products, it is to use inspection and maybe have a WAF and things like that. Then we need to terminate transport layer security and do the inspection. And if we just continue inbound using HTTP, that was quite common to do perhaps early on, to have a firewall and then have a clear text traffic on the internet, on the intranet. And yeah, that might be fine if it's small like here. It's just one API, but in reality, it often is a lot of more things on the inside. So then we get a quite big unsecure intranet where it's clear text traffic. And if an attacker gets foothold within the network, it can read and modify the clear text traffic. So we of course need to address this. And a solution to this is to do like this, to re-encrypt inbound traffic. And so that we would regard, you could either use pass-through or re-encrypt, and we regard that as good end-to-end, even if it's not true end-to-end perhaps, given that we protect the node that does the re-encryption properly, so no one can get foothold there. But that's assumed. So this is end-to-end, and we also have the benefit of using the security features in the firewall or gateway product with inspection and such things. So yeah, and one more thing here. You could think maybe that sounds a little bit old to have an intranet with the HTTP, and a more modern version of this is a Kubernetes cluster, which grows over time, where you put more and more stuff in, and because the sort of default behavior there is to terminate TLS at the ingress controller, and then you sort of get a more modern version of the problem. So be careful with that. So moving on, that was end-to-end. Now how about authentication? So we have two parties, the server and the client. And do we get server authentication with the transport layer security? Yes, that's by default, and that's what we usually see in the web browser using HTTP. And but here it's machine to machine, and we also want to authenticate the client in a secure way. So do we get that? Well, not by default, but the protocol has support for mutual transport layer security, or MTLS for short, but we need to configure that and give the client a client certificate which it can use. So we do that, and this is great. For now we have end-to-end confidentiality and integrity of the request. We have strong server and client authentication, and if we do it like this with the firewall, we also have defense in depth, and sort of the problem is solved. We have a secure system integration. So why don't we do this all the time for everything we do? Are there some issues here? Well, we talked about the end-to-end aspect, and how that could be trouble depending on how the network is and implementation details. So you need to understand where TLS is terminated and so. But that we have addressed. And then the mutual TLS is really good, but it's not for everyone. In a large organization where you don't have built up or invested in public key infrastructure, managing a large number of client certificates can be quite expensive and time consuming. So it's not that commonly used. But if you are an organization that have all that, then it might be easy to just start using mutual TLS. And then also we have only done authentication. We really don't have any good support for fine-grained authorization, which we usually need for APIs, because there are a lot of APIs and we want to restrict access more fine-grained than just based on the client ID. So we need to do this, and we will now address different client authentication methods. And we have some weak ones and some strong ones. The old ones, API key and basic auth, which we do in the application layer, they are regarded as weak since it's a shared key or shared secret, and the strong ones are asymmetric, and there we have mutual TLS. But as we said, that's not for everyone. So is there an alternative for us if we want to do asymmetric client authentication? And there is one that is kind of new, but it is part of the security profiles for OAuth and Openly Connect, and it's so it is regarded as a secure industry standard method, and that's called private key JWT. And without having public key infrastructure, the client just generates a private public key pair, and then it creates a JWT where the subject is the client ID, and then the server can authenticate the client by validating that JWT using the client's public key. So it's quite similar, but it all happens in the application layer. So there needs to be some work done in the applications. But it's good. But of course, you also need to distribute that client public key and register that. So you need to build some kind of infrastructure around that, of course. So it doesn't come for free, but it's there and it's possible to use. So we have two strong, good methods to use. And now we can sort of say that we have solved the client authentication problem because we have good ways to do that. So moving on to the authorization part. And we have not addressed authorization yet, but before we do that, I just want to say if it's just as simple as this, we just have one API endpoint and one client, then we don't really have to do any authorization, because if we have authenticated a client, it has access to that endpoint and we're sort of done with authorization. We don't have a complex access model that we need to do any fine-grained authorization. But often reality is much more complex than that, and we need something that can handle this in a good way. And and you could also, of course, argue that you could do more fine-grained things with API keys and building around that. But if you do that, and you should support least privilege and key rotation, then you might build sort of a poor man's OAuth client credentials anyway. So we will look at OAuth client credentials, and that's industry standard for dealing with authorization. And it looks like this. So we introduced the authorization server, and so we have the API and the client just as before, and we introduced the authorization server. And now the client authenticates with the authorization server using a strong method, preferably like mutual TLS or private key JWT or maybe basic auth. And then it gets a token back, and then it can use that token to access API and server resources. So it attaches the token with every request. Very simple flow and standard for machine to machine. And it's good that we don't have to deal with these complex redirect flows that we have when users are involved. Today everything is simple, so that's good. So let's say that we have had a system with API keys and basic auth, and we have refactored to OAuth to increase the level of security. And then we look at the requests from a resource server point of view from the API. And the API gets the two on the top is sort of the old one with basic auth and the API key. And then the third one is the new one, the more secure one, the OAuth one. And if we strip away everything, it looks like this. It's a header with a secure string, and we have implemented all this correctly, so they are cryptographically secure. So then you might wonder, which is most secure? What's the difference here? It looks pretty like the same, and it is, because if you have that string, you can just use it and make a call to that API endpoint from another client, and that will work perfectly fine. So this is sort of the bearer scheme here, is that if you have the token, then you can just use it. It's not tied to the client in any way or the request. So that is a weakness. So what have we actually gained by introducing OAuth in this solution that we had? Well, there are some OAuth features, and the first one I mentioned is that we now have a sort of industry standard solution. There are RFCs and specifications and official threat models when you implement this. There are good support in framework, so you don't have to do everything yourself. So that's really good. And we also have support for fine-grained authorization, since access token, they can contain metadata and like OAuth scopes, and we have more information to base our access control decisions on. And access tokens can also be made short-lived, so we follow the principle of least privilege and so. And having an authorization server and token also helps us having support for client secret rotation without downtime and because it's not dependent on, the resource server has no dependency to the client secret, so we can rotate it. Given that the authorization server supports a good way for us to rotate the client secret, perhaps automate it or do it easily by just manually. So, but if we don't use these features, then it's quite similar to having an API key. That's so if we have tokens that's just valid for all APIs and don't use the scope part, then we haven't really gained that much, perhaps. So that's important to understand, that we must also use the good OAuth features that we now have access to. And this is, of course, nothing new. The bearer issue that I showed you, it's oh, sorry, I forgot one, the most important one. We also have support for something called proof of possession token, which is a stronger way to deal with tokens. We will talk more about that later, so we don't use this bearer approach. Because the bearer issue, it was recognized from the beginning in OAuth. This blog post is maybe hard to find now, but you can dig it and find it. And one of the that was part of the initiative doing OAuth 2. He left that project because he thought there was a lot of security concerns with it. And even if bearer tokens is not the road to hell, perhaps at least not yet. So it's fair to say that the concerns here are valid. And if you, the last part here is a good read. So OAuth in the hand of developer with deep understanding of web security is likely to result in a secure implementation, but in the hands of most developers, it's likely to produce an insecure implementation. And so it's obvious here that we need to harden OAuth, we need security best practices, and we need security profiles. And one of the most commonly used and most well-known is perhaps FAPI2. And that's for financial grade APIs, but that's just financial grade, so it's valid for any domain that has high security requirements like healthcare and so. And if we look at the requirements here, the 4, 5, and 6, we can see that shall only issue sender constrained access tokens. So we will look into that. We have also talked about mutual TLS and then there's this new term here, demonstrating proof of possession, that we will talk about. So and we should only authenticate using those asymmetric methods. So this is well defined how we do secure OAuth. So of course we should apply this if we have a system that requires high security. And mentioned sender constrained access tokens a lot, and now we will look into that. And there are 2 ways to do this, mutual TLS or demonstrating proof of possession. So we start with mutual TLS, and it looks like this. It's still client credentials flow, so nothing much has really changed. The difference here now is that since it's mutual TLS, we are restricted to use mutual TLS for client authentication. And when we do that, then the authorization server, by the specification, will add the client certificate thumbprint in the CNF claim and then sign the access token. And then the client is now required to also do mutual TLS authenticating to the resource server. And then the resource server can compare the client certificate thumbprint that was used for the client authentication with the hash in the access token. And by doing this, if someone steals that access token, that secure string that we were talking about, then and try to replay that without having access to the client's public-private key pair, then that will fail. So this is a much stronger solution. So now the token can't be used by anyone. It's sender constrained to the particular client that has access to the private key. So that's good, but as we said previously, not everybody can use mutual TLS, and so the alternative is this. And this is kind of new, and there are products like the Identity server and some other solutions that has started implementing this, but maybe it will be more standard in more products in a year or so. So it's called demonstrating proof of possession, and it's still client credentials. So the request flow is the same, and it's similar to the mutual TLS that we just saw. But since now we don't do it in the transport layer, so we need to do more work. We do it in the application layer. So this means that the client generates a public-private key pair, and then it creates a JWT, and within that JWT, it ties that to that token request, and then the authorization server will validate that and now embed the hash of the client's public key in the same claim as was in the mutual TLS flow. So it's quite similar. And then using the same key pair, the client can now create a new DPoP proof, but now it's tied to the request to the resource server, and it also embeds the hash of the access token in that, and then it sends both those JWTs to the resource server, both the access token, which is just a normal access token with the CNF claim, and then also the DPoP proof. And then the resource server needs to validate both. So it validates the DPoP proof and the access token, and now it's tied to that particular DPoP proof. So nobody, without having access to the private key, can use that token from someone else. So we don't want to go into more details here. There are more details. It's just to get an understanding that there is an alternative to the mutual TLS thing, but there are good resources to read about this, and I find those useful. So you can read more about it there. And good. That was sender-constrained access token. So there's a lot of security that we can start using by introducing OAuth. So we have now both zero trust, defense in depth, and least privilege that we're using to limit the scope for each token that we use. And so we have this. We have network segmentation, if we can use that. Some APIs are of course meant to be public, so we can't. But if we have done that properly, and then we have the end-to-end TLS properly configured with strong ciphers and so. And we are using mutual TLS and proof of possession tokens, and we have the fine-grained authorization. So it's a pretty strong solution. And I just want to indicate with the blue border here that it's important that we also evaluate and authenticate the request at the resource server. So we don't terminate that in a gateway, and then because then we might have a misconfiguration issue or something like that. So it's a strong solution all the way. And it's time to do a little summary of the HTTP APIs integration that we looked at, and then we will look at some other kind of integrations. But so if we summarize this, we apply proper network segmentation, strong TLS, and we have strong methods, and also the fine-grained authorization that we talked about. So So we have all this, and that's a lot of stuff, right? So you might starting to think, oh, should we always use everything all the time for every integration that we have? There's a lot of stuff, and it's different. Some are banking, and some are just some retail, and we can't just. Should we have everything? Of course, it depends. So that's the obvious answer here, and it depends on the sort of the threat model, what you're trying to protect, and budget, and perhaps compliance and regulations and things like that. So, but it's important to understand what you have, the tools we have to secure this, and then if you choose not to use any of it, you're aware of that and the risk, and it's a sort of an accepted risk for you. So if we look at it in a little bit more general way, before we move on to other kind of integrations, so we can form a security baseline for system integrations. So we always should think of these 4 key aspects. The network segmentation, the transport layer security, and the client authentication methods, and how fine-grained we need to do the authorization to not leaking data between customers and things like that. So with this knowledge, we will now look into 3 more other kinds of integrations. So we have sort of done HTTP APIs, and next we will look into file transfers or sharing files, and also messaging, putting events on a message bus. But still, it's just client to server. So we had this, the baseline here, those 4 protections. So let's say we are in a financial grade environment where it's worth investing in mutual TLS and proof of possession tokens. So that's our security level that we want to have in every integration that we do. So and that's secure. But then we get a feature request that we need to serve files, and it doesn't really fit that well in the API perhaps. So we want to use some good file storage, perhaps an S3 bucket or Azure blob storage or whatever. So then a common solution is perhaps that the API serves a secure link to that file, and then the client can download it. And if we just do it like that, then out of the box, we usually around those services only have transport layer security and this secure link. And if someone has the link, they have access to the file, and then it's really not that sender constrained anymore, because it's more of a bearer token API key thing. So we have a weaker path to the data here, and the file might contain a lot of sensitive data, so it's worth protecting just as good as the API endpoints. And the obvious solution here is, of course, to do like this. Just serve everything through the API, and then you know that you have the same security and make that storage internal on the private network. But maybe that's not an option for you, perhaps for security reasons or performance reasons or something else. So we need that, and then we need to work with that and mitigate the risk. So we sort of have the same level of security. Perhaps we could add the same kind of networking protection, and we could also work a little bit more with this secure link, making it perhaps one time or asserting that it's only valid for this particular item, so we don't have any issues there. And perhaps the gateway here in front of us could require mutual TLS, because we know that the client has a client certificate to do mutual TLS with the authorization servers, and then it could also do it when it should access files. And then, of course, maybe we can't do the sender constraining properly, but that's a risk we can accept given all this. So we feel confident that we have the same level of security in both those integrations now. And but then not everything is a perfect fit for HTTP, right? So we know that in a large enough organization there will be FTP and XML somewhere. Some integration will use that, and the way to secure that is to use secure FTPs, of course. We need to think in the same way here with the network protection and using good quality SFTP, and having, of course, the least privilege configuration for the accounts that we use, and also using the client certificate authentication method, even if it supports username password. So with that, we sort of get the same level of security here, and we can feel confident that there's no sort of weak way into our sensitive data. And then we have the message bus, and we can do what we can there in the same way with the network segmentation. We have good transport layer security, and we try to do strong client authentication. We can use that, and then we need to do least privilege configuration for the topics and queues in the same way as we had worked with scopes or FTP accounts or file access. And maybe also we need to consider message signing, because if there's a lot of people putting messages on the same queues and topics, how can we know which client put which message, right? So we might need to do some more work there. But and when we're starting to see this map, we realize that securing one of these paths is not that hard, perhaps, but securing all paths all the time, forever and ever, that is hard. And you're starting to realize that complexity is really the enemy of security, and it was stated and put very well by Bruce Schneier in 1999, and the headline there is "You can't secure what you don't understand," and I can really recommend reading this. And a way to, because that's one of the problems with integrations in large solutions, is that you sort of lose track of them, and maybe you don't, after a few years, you don't have a full understanding on how the system works and all the ways you can access the data, and you have some weak ways that you're not aware of. And one way to keep that understanding is to work with good pictures of the system, just the classic system diagram, and that shows the sort of important security aspects. And so we get an understanding of what it is, what's hosting our API. Here is Azure icons. So for those knowing Azure, it's quite obvious what this is, that it's an app service, it's not a Kubernetes cluster, and we have some private networking going on. We don't have to go into details there. And the blue zone is to show that here we have network protection, and in the yellow we don't have it. It's public, and as you can see, the message bus is publicly accessible. And that's perhaps of budget reasons, because it's expensive to do private networking in Azure for message buses, or it's misconfiguration, and we're not aware of that. So this is the strong solution that we talked about with mutual TLS and all that. And then we get a feature request. So we feel pretty confident here, because the managed identity there, that's a strong way to authenticate. So it's hard to, even if it's public, it's hard to get access to the bus. And then we get a request that this client should have access, and it's quite easy to solve that. It's just give it a key, a connection string, or a SAS key to that service, and we're done. So, and then all of a sudden we have this strong solution, and we have this weak way into our perhaps most sensitive part of the system, the message bus, where you can maybe control everything that happens. So, and when we analyze this as an attacker, we see that we have those two ways in, and the one is protected by that client certificate, which is really hard to get, and the SAS key may not be that hard to get. It might be checked into repos and things like that. Certificates are sort of easier to treat in a good way. And if we add this attacker perspective, this is called threat modeling as well, and that's usually the way you do before a penetration test, or in the beginning, to understand the system, to understand the weak spots, and then So that's really, really good to do as a team and keep updated as you add new integrations, so you understand all the communication parts and how strong your solution is. So the solution here is, of course, or you could do like this, or once again go through the API, and that's the way you access the message bus, and then so you mitigate the risk there. And then you will have this attacker model, and it's easy to analyze and easy to understand. Yeah, another way to look at to get an understanding of the security. This was sort of from the architecture's perspective and a little bit of networking, but maybe from a developer point of view that's building the API. This is a way to understand the system where we should, with zero trust, we should have APIs that are secure even if we don't have any infrastructure protection. So we don't have that in the picture. But all the protections that we built for API, the token validation and things like that, we put that as early as possible in our application layer, so we deny requests early. That's good, and that's commonly built that way. And so if we take a look at, we have an endpoint, in this example, we have a get product by ID endpoint. The code in the application layer, it looks like this. And as we can see here, we have, this is .NET and C#, but in other languages it looks quite similar. So it's just example code here. But we have some sort of function level access control with some attribute. In Java, that would be a pre-authorized tag. Then we have input validation. That's good. And we have object level authorization. That's something that a lot of people miss. That's why IDOR or BOLA, broken object level authorization, is number 1 on the OWASP top 10 list for APIs. But we have it. We know how to do this good. And then, so that's the application layer. And then we sort of do the domain logic and accessing storage or the message bus that we do in the service layer. But we really don't do any security there. That's just business logic and getting data efficient. So this is our solution. And if we look at that, then our trust boundary will be like this. If we have just had the storage, and that might be fine if it's just an internal storage that we are the only ones that use. But then we add this message bus, and then our trust boundary grows because the message bus listener, it just uses the domain logic and the service layer. It doesn't go through the API, the application layer there. So that's included in our trust boundary as well. And in larger organizations, there can be a lot of clients putting messages on the bus. So that this might simply be too weak for us. We can't have this big trust boundary. It's starting to grow like the insecure intranet that we sort of laughed about early on, or the big Kubernetes cluster. So we need to mitigate this risk, and then we can do some refactoring in the code. We still have the function level authorization, and we have the input validation for early return. But we have moved the object level authorization because that's often tightly related to domain logic and things like that. And now we have put authorization and validations in the service layer as well. So if we look into the service layer, then it does the same data access as before. Nothing has changed really there, but we have added function level authorization. We have input validation, since we're using strongly typed domain objects and entering this function. We don't allow any strings that's unrestricted. And then we have the object level authorization as well. So with this code, we always know that we will do proper authorization, even if this code is triggered from a service bus message or if it's triggered from an API call. So with that, we get this blue border and we get a much smaller trust boundary once more. And that's good to understand what's within your trust boundary. And one thing to note here, We should, of course, have the infrastructure protections and the firewall and gateway, even if we build a strong solution like this. It's defense in depth. You can see the layers here, multiple layers of security. And that means we are doing the function level authorization twice within the API, or perhaps even a third time if we, in the gateway, validate the token and route based on scopes. A web application firewall might do some input validation that we also do in the application layer and also in the service layer. And that is usually not a problem. Sometimes you might need to work on performance for certain applications, but often it's not a problem. It's a strong solution, but once again, it depends on your context, your threat model, if it's worth investing in multiple layers of security. But for high security applications, it's definitely worth to have a strong solution. So that was trust boundaries, and we have now a really strong solution where we enforce this for every type of integration path we have, and we have strong patterns that so we can feel pretty sure that that happens. So what can go wrong now? We have a really good design here for secure integrations. So the thing that can go wrong is, of course, implementation, that we do some mistakes and we do some bugs. So really, really important thing for secure system integration is to verify that this works as expected. So when we start penetration tests, we often ask the client what they sort of fear, and a lot of clients, they say that we don't really, that we leak data between users or customers or to third-party integrations, and then we look for what kind of testing do you do to verify that this won't happen. And a lot of time those kind of tests, the test categories here, that's from OWASP, the Web Security Testing Guide, they're really missing. So I want to show a good example of one kind of test that it's easy to do. Is this the so-called negative test case, that we should return forbidden if we don't have the correct scope. And as penetration testers, that's of course something that we will try, and sometimes we succeed, and then it feels a little bit unfortunate if the team building the API haven't done this kind of test to realize that it's not perhaps that much work to do. So don't wait for a pen test to find those authorization bugs. And and other good resources for verifying security that we often refer to is CIS controls, which sort of is for getting the full picture of security, because it covers things like service provider management, account management, the life cycle of an integration, that you onboard it in a good way, that you monitor it during usage, and that you decommission it once you don't use it, you don't forget about it, because that's also a common mistake, that old service and integration endpoints, they just stay there forever, even if they're not used, and then you have an unnecessary large attack surface. But CIS control, it's good, and it has also good guidance for how to harden infrastructure and things like that, but it doesn't say really that much on how to build secure application or application security. For that, we often refer to OWASP ASVS, and if we're using OAuth, then we have the best current practices, RFCs, and the FAPI security profile that I showed you earlier. And with all this, we will have a really good security baseline and guidance, and we of course need to apply the parts that are relevant for the integration that we are building or the context that we're in. This is also a good way working with security, is in this structured way. It's also a good way to meet compliance requirements, and you're able to show that your solution is also compliant, because that might also be an important requirement that affects your security, that you must use certain authentication methods and cryptos and things like that. So with all this, we have a design that is both secure and compliant, sort of. And given that all tests are green, that you can see here, we have done this. I want to point out that we have talked a lot about confidentiality and integrity, but the last test category here, load test and performance. Availability is also an important aspect of security, and for some integrations that might be maybe the most important part, that the integration works and the service responds fast, and so you have tests that shows that you're not easy to have denial of service attacks, and that the scale out works, and that the DDoS protections is in place, and things like that. But let's say we have done all this, then it's fair to say that we have integrations that are secure and compliant by design, and that's pretty good. So it is time to summarize. So yeah, to define a security baseline, and I think these are the 4 key aspects that are valid for any integration. To sort of think of, can we restrict something with network segmentation? Sometimes you can, sometimes you can't, but a lot of times maybe you don't need to expose integration endpoints for everybody on the internet, just for your integration partners. And assert strong transport layer security, understand where it's terminated and where it's re-encrypted, and how strong transport layer security you actually have, all the way from the client to the server. And assert strong client authentication methods for all requests. That's of course really important, and even if you don't have high security requirements, so you can't use mutual TLS or this new private key JWT thing, then you could sort of harden the basic authentication thing by using random good secrets and rotating that might, and proper key management. So there's a lot of work that you can do there to mitigate risks, even if you can't use asymmetric methods. But because if you use those, you still have to rotate those certificates, so that problem don't go away. And then also use fine-grained authorization for all requests, and have this close to the application core at the resource server, so you don't assume that other things have done important security validations for you. Apply both zero trust and defense in depth. And then we also, the importance here, with integrations, one is easy to manage, but in a large organization there are maybe hundreds. So if you can reduce complexity or keep complexity under control, have good architectural diagrams and threat models so you understand the whole system and how integrations works, and know your trust boundaries, and do those technically detailed threat models. And the last thing here, verify that it works with tests. Don't wait for a penetration test to find misconfigurations and bugs. There's a lot of security focused testing that you can do by yourself, by looking into those security frameworks like CS and OWASP, ASVS. There are of course a lot of frameworks that can help you, but those are good examples. And so, thank you.